All right, we're starting. So, last time we looked at a new kind of integral. It was a line integral over a vector field, I believe it was called. We looked at f dot dr. So this is just recalling from last time. Okay. Can you tell me the steps to compute such an integral?
Find R2.
So you find r, then
Find dr.
you find dr, right, which you just differentiate r. Then
Find f2.
plug in your parameterization into the given vector function.
Integral. Dot product.
Right, now you dot product them and you integrate. So you take this guy, dot product with that guy. And then 5 is to just integrate that. Right, and the limits would be directly depending on the parameterization you got. So a couple things that was good about this integral is, one, we learned that it could be expressed as a sum of integrals of this form. You know, and maybe you might have a third variable, you might even have more depending on the situation, but it's actually equivalent to that form. You could actually break these up. If you thought of this as, you know, like P2R, and then that's your dx, dy, dz being dot product. And you have the same kind of thing here. What was another interesting thing about this integral? Huh? It's the work integral. Right, so this gives the work done in moving a particle or some element along R in the vector field F. Okay? So that's what we did last time. Very important integral. And it's not the last integral we'll be looking at, but we're actually going to stick with this kind of integral for a while, the line integral over a vector field, because there are some very important properties that we can have depending on the properties of the vector field itself. And that's what we're going to talk about today. So that's what brings us to 13.3. It is, right? This is called the Fundamental Theorem. Of line integrals. Similar to the fundamental theorem of calculus, in fact, it's pretty much analogous to it. And we'll be looking at other such theorems. But it's a very important theorem that deals with line integrals, and it's called the fundamental theorem of line integrals. So you might have recalled, for example, when you're looking at one of the fundamental theorems from part 2 or part 1 of the fundamental theorem from Calc 1, it was saying that if we integrate some function on some boundary, then the result of that was big F of B minus big F of A, where F prime was equal to F, right? And F was continuous and all that stuff, right? So that was the fundamental theorem of calculus, one of the versions. And we're going to have a very similar thing with line integrals, it turns out. So basically, it turns out and I'm not going to prove this, but the proof isn't that hard. You can see it in your textbook and it's not that big a deal. But we can think of something like the gradient of f as a derivative. And f as its antiderivative. And we can get the following, which is called the fundamental theorem for line integrals. it's really neat how this works out. If you can just change your definition of what a derivative is, and you can get some nice theorems that fall out of this. And that's going to be a common thing that's going to happen. We're going to do that like 2 or 3 more times, and we're going to talk about what that means for the general theory of calculus. But for now, let's actually write down the theorem. Now I'm going to tell you all the conditions that need to be fulfilled for the theorem, but some of you should know, but usually in this class, if I'm giving you such a problem, all these little things in the background would normally be fulfilled, so you don't really have to check them. So the theorem says, let C be a smooth curve. Right, which is again something, if it's in this course, I'm going to either giving you a smooth curve or something that's piecewise smooth that you can break it up. So, but it has to be smooth for this theorem to work. And again, you can parameterize it by R. For some limits here. And suppose we have this function f, which is differentiable and continuous. Meaning we can find its partial derivatives and continuous on C. Then the following is true, and I think I have space for the equation here, so I'll just write that. If I take the line integral over its gradient field, dot dr, right? The same kind of integral, same kind of f dot dr integral, computed in the same way, except my big F is now the gradient of some function that I have. Then it turns out that is going to be equal to its antiderivatives evaluated at the endpoints, and then I take the difference of it. So that's going to be the same as the original function evaluated at the final point minus the original function evaluated at the initial point. And that equation, under these conditions, is called the fundamental theorem for line integrals. And in studying that equation, we're going to learn all sorts of neat things. About vector fields and line integrals over vector fields. Okay, but that's a very important equation. So once you are actually integrating f dot dr, where your f is actually a gradient field, it turns out that when you're going along a curve, that whole process that I had you guys write down, what are the 5 steps to compute these, it doesn't even matter anymore. You don't even care. It turns out you can just evaluate the original function at the end point. Notice that here this is the end point, the final point. And the initial point, you can subtract them, and that will always be equivalent to actually computing that integral. This is called the fundamental theorem for line integrals. Okay. So that's some pictorial illustrations here. So that's basically saying whether I'm in 2D or 3D illustration. If I'm in 2D or 3D, so I can have some path, right, in some sort of vector field moving from A to B. Or I could even be in 3 space, and there's some curve over here doing its thing and ending up over here. It's a smooth curve or a piecewise smooth curve, where this is the point A and that's the point B. in this case, if I take the line integral along C, this is my path C of my function, the gradient of some function dot dr. That's just going to be my f evaluated at this point, which can be, you'd actually plug in the coordinates here, right? So it's like x2, y2 minus f of x1, y1. All right, plug in the initial point to that function, plug in the final point of the function, you subtract them. Similar thing here. The gradient f dot dr of that guy is going to be our function times x2, y2, z2 minus the function, and you plug in x1, y1, z1. So one, you should know that you can do this, but we are going to talk about how do you know when you need to do it and how do you actually figure out all the pieces that you need to actually apply to this formula. And then we'll also talk about some consequences that fall out of being able to do this. Just want you guys to understand the idea. And the important thing is only the endpoints matter in this case. It does not matter what the curve does in between. It just matters what is the value of the function at the first point and the value of the function at the last point, and that's going to be very important. There will be times, and I'm warning you that I'm going to do this, where I'm going to ask you to actually compute some line integral, and the curve itself is going to be very complicated, where it's going to either take a very long time for you to compute it, or it's going to be impossible for you to compute it directly. And the trick is, you need to realize that you're in this situation and you need to subtract these ones. Usually, such questions, though, they'll be in two parts, where one part kind of hints to you that, okay, in the second part, I'm going to kind of need to use this idea. But we'll talk more about those. I'll give you such an example towards the end of this section. Okay, but that's important. Now I have to introduce some terminology, though, that we're going to be using. Tell you some other cool theorems, and then try to get to applying this theorem. So I'm going to introduce the phrase independent of path, which is basically what this is. The value of this dot dr will not change if the path changes. Right? So if I have, here's my point A and over there's my point B, it doesn't matter if I do a straight line segment, go along the arc of a circle, do some wavy thing and get to that point, it doesn't matter. All of these points will actually give me the same answer because the inside doesn't matter, only the value of the function at this point and that point matters. So it doesn't really matter how I get from point A to point B. The integral will always give me the same answer. Such an integral is called independent of path. So if we're doing we're integrating, finding the line integral over a vector field, and we find that it doesn't matter what path we choose to move along this vector, to calculate this integral over a certain path. It just matters where do we start and where do we end. We call the vector field independent of path. Right? So the path, it's not dependent on what route we take. It just depends on what's our starting point and our ending point. This also means something very different, something very important. So we're going to talk about what it means for a curve to be closed. Closed means the initial point and final point are the same. So we say a curve is closed if when I start here, I can do whatever, but then I end there again. Such a curve is called a closed curve. Now if we have a piecewise smooth closed curve, what this means is then what would that integral mean in this case? What do you think? 0. It would be 0. It would be 0 because that's going to mean it's the function evaluated at the end point minus the function evaluated at the initial point, but these happen to be the same points. So you just take that, you subtract itself. Okay? So that's another property of vector fields that are independent of path. If you take a line integral of them on a closed curve, the answer will always be 0. Provided all the conditions I mentioned before are fulfilled, right? They're differentiable, they're continuous, and the path itself is piecewise smooth. So that's going to be a very important thing to know.
It's differentiable because you have put indifferentiable. You got 2 or 3 variables that are indifferentiable on the original.
Differentiable. I mean, I can differentiate. Because I have to be able to create a gradient, which means I have to take the partial with respect to x.
In the original theorem?
Differentiable is the word. It has to be differentiable.
Okay.
I don't even think indifferentiable is a word in calculus. If I wrote that, that's the flu talking. That's not me.
Blasphemy.
Huh?
Did we get points for the blasphemy?
What's a blasphemy?
Writing indifferentiable.
That's not a blasphemy. Blasphemy is defined by what's on the syllabus. We follow the law here. That's the one that's written on the books. You don't just make up, oh yeah, that's a blasphemy. You can't just make them up on the spot. It's written, it's in black and white. Okay. So it's differentiable. It means because we have to be able to find the gradient, so we have to be able to take partial derivatives. Okay, what else do we want to say? Okay, that actually gives us a theorem. So that's something, another nice thing that we should know. So there's a theorem that talks about this. The integral and this one is slightly a little more tricky to prove. It's independent of path if f dot dr equals 0 for every piecewise smooth closed curve. So it turns out that whenever this happens, it means that the vector field you're working with is independent of path. If it happens for any smooth curve that you choose. So for example, so one application of this, I'll just mention this very quickly. So, for example, know F is independent of path, then the work needed to move a particle around a closed curve in F is always going to be 0. This leads us to another terminology. Which I've actually introduced before. That says F is a conservative vector field. Because it conserves work, it conserves energy. That's because if you're moving around a closed path, it'll literally take you no energy, no work to actually do it. So that's why it's called conservative. So I did mention before that we know that if F is the gradient of some field, is the gradient field of some function, then that means it's conservative, and now you're seeing why. Why did it get that name? It's because it takes you no work to actually move in a closed curve. Now I need to define a couple more things because I'm going to give you some more theorems that we'll need this for. So let's talk about definitions. I said D is called open if it does not contain any of its boundary points. Example. The set of points x, y such that x squared plus y squared is strictly less than 4 is an open set. Right, so these are just the guys. They're contained in the circle of radius 2, but they do not contain the boundary of the circle. Right, so this is not a part of the set. They're literally just all the points on the inside of that set. There are many things that in calculus they only work on open sets, so it's very important for us to know what that means. We can also have another definition about connectedness. D is called, it's the same, D stands for domain, it's just talking about some region that we care about, our function operating in. It's called, there are many different kinds of connectedness, but in this class, whenever I talk about things being connected, I'm going to be talking about them being path connected. If any 2 points in D can be connected by a path that lies completely in D. So if I have a set like this, that's a connected set I can think of. Because if I pick any 2 random points in such a set, I can connect them with a path that lies in the set. So such a set is connected. I can look at another example where I can think of a set, but I think of it as a union of 2 groups of sets. So let's say here I have some set hovering over here, and I have some other set hovering over here, and then I take the union of them and I consider both of these sets together to be one thing, it turns out this is not connected. Because if I pick a point here and I pick a point here, to connect them with a path, I have to exit the set. Right? So this means, basically, connected means it's not in pieces. Everything has to be together in kind of one blob. So there are some times our theorems will fail if the set that you're looking at is like fractured or fragmented or disconnected. Another definition. Curve is called.
Professor,
Yes.
what is this example, the set of points x, y, z?
Yeah, it's a set of points that are inside the circle of radius 2. But
What is the
because we're
y?
strictly less than
Okay.
because we're strictly less than 4, we're never actually equal to 4. We're not equal to any points on the boundary. So we don't have the boundary, it's just a circle and inside. And such a set is called open.
Okay.
So I'm going to tell you some theorems that it only works on open sets that are connected, and the curves that we're connecting them with are called simple. So a curve is called simple if it does not intersect itself. Except perhaps at its endpoints. So we can have example of simple curves here is like this guy is a simple curve, this guy is a simple curve, curve that goes around and is closed is a simple curve. We're not simple. If the curve crosses itself, and we're not talking about being at its endpoints. So the curve can do this. It's also not a simple curve once it crosses itself. I think one more technical example, and then I can talk to you about some theorems that we're going to be using in order to apply the fundamental theorem for line integrals. To know, for example, when we can apply the theorem, and then try to figure out how to actually do it when we know we can do it. So, another definition here. Set D is called simply connected. If every simply closed curve contains only points in D. For example, again, anything that's like one blob that's all together, that's going to be simply connected, because any curve that does not intersect itself but has the same starting and ending point, it will only include points that are in the set itself. you can think of another way. Another example though. Here's a path, but there's like a piece in the middle that's missing. And I can take some random closed path in here, but you'll notice that in the interior of that path, there are points that are not in the set that are in the middle of that path. And that's bad. Basically, simply connected is a way of saying it has no holes. Because that is something that will actually void our theorems that we're going to be using. There are things I'm going to tell you that if you're on a set that has holes that you can't connect without exiting the set, where simple curves, closed curves don't behave this way, it turns out that the theorems will be wrong. They won't actually work in such cases. And I believe in some of the suggested problems in the homework that I have in the syllabus, you'll have cases like this where they'll ask you to compute something in two different ways that should give you the same answer, and you realize they gave you the different answer, and then they'll ask you what's wrong. And it's usually going to be one of these reasons. Okay. So we have some very nice theorems, but the cases in which they work are very particular, and the sets on which they work on have to be very nice. Yeah.
Can you explain again why that's not simply connected?
This one?
Yeah.
Because these sets here, this is a gap. These are not in the set. Right? The set is the shaded part that I mentioned. Okay? Here's a closed path. That's completely in the set, right? It's in the shaded region, right? But if I look on its interior, there are points in here that are not in the set D. So the path contains points that are not in the set that I care about.
Okay.
In other words, something like that will always happen, and it's always possible to happen if you have a hole or a gap. And that kind of voids a lot of the things that we'll want to do. Yeah.
Wait, that is a closed path on the other side.
Come again? These are both examples of
No,
closed.
I'm talking about the other side, not simple.
Yes, this is closed
So why is it not simple?
because it intersects itself.
Okay. Oh, okay.
Simple means it does not intersect itself.
Okay.
So here are our theorems. There are going to be two of them. I think here's where I ended. So let's put it here. Suppose F is a continuous vector field. On an open connected region D. And F dot dr is independent of path D. So this is a condition that we can, it's not easy to check this in practice, but it is an important thing to know. I'll give you some criteria that are easier to check if you actually know a formula for your vector field. But you can know that if this happens in any open connected set, then this is a conservative vector field, meaning it is the gradient of something, which would mean that the fundamental theorem applies. And another theorem says, this is kind of something you can only apply in like 2 dimensions though. If your function is, let's say, PQ, these guys are functions, right? These are functions of x and y. On an open and simply connected so I have some vector field that is a 2-dimensional vector field. It's on an open set that has no gaps, no holes, and it's not in pieces. So it's connected, it's simply connected. P and Q has continuous first order partials. And it is the case that if I take the partial of P with respect to Y, that is equal to the partial of Q with respect to X throughout D. That's going to be a very important equation, remember that. That'll be important for us in Green's theorem and some other theorems. Then, F is conservative. So this is a criteria that is not that hard to check. So you would be given some vector field. If you notice that, okay, these guys are continuous on some open, simply connected region. So I can just describe the path that I'm giving you. And the set that I'm giving you on. Let's say you have this vector field that's 2-dimensional, and you notice that if you take the partial of the first component with respect to y, it's equal to the partial of the second component with respect to x. And that's happening no matter where you are in this set. Turns out that f is conservative. And by f is conservative, that means there is some function that it's great. If I take the gradient field of it, I get f.
Question.
Yes.
Are we gonna see any of these like in math example problems
Yes.
today?
Yes. Just trying to be thorough.
This is a textbook that we just wrote. We've been writing for almost an hour straight. Everybody in here is sick. I feel like I'm in an in-computer. I'm ready to go home.
These are those small examples here. Determine if f is conservative. Hey. So we're going to give you 2 vector fields. 2x plus y squared. 2xy. B. F is equal to 3xy plus y squared, x squared plus xy. Okay, so let's do the check on A. What can we say? Here I can just call this P, 2x plus y squared. My Q will be 2xy. If I take my partial P with respect to y, what would I get?
2y.
2y. If I take my partial Q with respect to x,
2y.
2y.
So that's a conservative.
So that's a conservative vector field. And since these are polynomials, since these are all polynomials, these are polynomials. They are continuous everywhere. This means that our f here is conservative. That means a bunch of things. It means it's independent of path if I'm doing f dot dr. It means if I integrate it on a closed curve, the answer is going to be 0, so I literally don't have to do anything. It also means that it is the gradient field of some function that we will be able to find, but I didn't really tell you how to find them yet. But that would also mean that the fundamental theorem for line integrals would apply to this function. What about B?
3x plus 2.
So this is 3xy plus y squared. Here my q is going to be x squared plus xy. I can find my partial p with respect to y. It's 3x plus 2y. If I take my partial q with respect to x, it's 2x plus y. These are not the same. F here is not conservative. Which means this guy's not independent of path, so depending on what r I give you, the answer for the integral is going to change. It means if I integrate it along a closed curve, it's possible to not get 0 as an answer. It also means that the fundamental theorem for line integrals would not apply to this vector field. So let's recall something I did mention before. So if our function is equal to the gradient of some, it's a gradient field for some function, f is called the potential function, right? And the question is, how do you find this function? So let's say you discovered something about this f, like for example, you have this function here, you realize, hey, it's conservative. So there are all these nice properties that you want to take advantage of. But in order to do that, you kind of need to know what function you took the gradient of in order to get that field. Right? You can say you want to find the potential function for the vector field. The question is, how would you go about finding such a thing? There are two main ways to do this. And I'm going to talk about them. Well, maybe I should talk about where they come from. So let's say f is pq, right? Where this is the gradient of something. What would that mean about the p and the q? It means that my p I can think of as what? Partial with respect to x, and my q I can think of as a partial with respect to y. Okay? So using that fact and noticing that pattern is what's going to help us come up with these methods. Right? So a method 1 is what we're going to try. This is actually something that if any of you have taken differential equations before, this is something you remember when you're doing a topic called exact equations. Huh? Yeah, so there was something called an exact differential equation where it was, if you have m times dx plus n times dy, and you know that the m was the partial with respect to x of something and n was the partial with respect to y of something, there was a way to find the solution to that differential equation. That's going to be method 1. And then I'm going to show you an easier method that you probably didn't learn in differential equations, but if you like doing it the differential equations way, that can work. So the question, the method here would be to start with the partial with respect to x, that is the p, to integrate to get f, 3, differentiate with respect to y to get q, and then 4, you integrate again. To get the original f. All the while, you realize that when you're integrating, you're picking up like arbitrary constants, but every time you differentiate, you can solve for those arbitrary constants. And then, while doing this, you'll pick up clues from the arbitrary constants. Right? So the idea here is you cycle through all the partials. You start with partial with respect to x, then you go to f, then you go to partial with respect to y, then you go back to f. And if there are more variables, you just keep going through that process. Then partial with respect to f, then partial with respect to y, then f, then partial with respect to z, then f, then partial with respect to w, then f, and blah, blah, blah. You can keep cycling through all those variables, and by the time you get to the end of the line, you will have picked up all the arbitrary constants, and you would actually know what your function is. So let's actually do that. And that was actually how you solved an exact equation back in Diff EQ class. Let's actually do that with, we'll probably do a couple more examples next class, but let's actually do that with the one we had earlier. So we knew that this guy was, we knew that that guy was conservative. So let's actually find his potential function. So using method 1. I know my partial with respect to x is going to be that 2x plus y squared. This means that my f is going to be, I'm going to integrate that with respect to x. What am I going to get? What would I get here?
X squared.
X squared plus
Y squared. X.
xy squared plus
C.
a constant, right? But it's possible to be a function of y, right? So if there was a function of purely y, when I differentiated with respect to x, it would have died and I wouldn't see it. So my plus c is some function of y, essentially. And so now what I can do, so I start with f, then move to f partial fx, then move to x, then now I want to take the derivative with respect to y of this function. Now the derivative with respect to y, that's going to be 0. This will give me a y squared. And then this guy will give me a g prime of y. And so what I do now is I have to set that equal to, wait, that's
2x.
2xy, right? And what I'm going to set that equal to is this guy, which is the q. And so now I have this equation, which means what? that means my g prime of y is actually 0. Which means my g of y is actually just some constant. Right? It's just some number. Which means I can go back to f and I can plug that in. So now I know that my f was actually equal to x squared plus xy squared plus some constant, because that g ended up being a constant, so I plug it back in. And it turns out that will be my potential function. So that's method 1. Should be familiar to you guys if you did 391 already. You would have seen things like that. How about method 2? Method 2 is pretty simple. Integrate with respect to each variable.
Excuse me, doctor.
Yes.
So you have f of y equal to 2xy. How do you get the g prime of y?
Because my f of y is this guy.
Okay.
So once I have that, I just set that equal to this guy. And that gives me an equation.
How do you get g prime of y? I don't get that thing.
G of y was right here. That's f.
Okay.
I found the partial with respect to y. That means I have to take the derivative of this with respect to y. That's where g prime comes from. I differentiated
So-
that line to get here.
So your 2x.
I started here, I integrated, then I differentiated.
Okay. Okay.
So the g prime comes from me differentiating this line.
So 2xy. Okay. Oh, okay.
And then once I differentiated, that gives me a partial with respect to y. I know that's actually equal to the second component.
Oh, okay.
So I set it equal here. That gives me an equation where I can solve for the g prime, the arbitrary constant ends up just being a regular constant. Okay. And here you sum the terms that show up. And that's the second method. You just basically integrate each component with respect to its variable, and then you add them together. So for example, you have this guy, 2x plus y. Is that y squared? 2x plus y squared, comma 2xy. I know that my f is actually equal to the integral of 2x plus y squared with respect to x, but also my f would be equal to the integral of this guy with respect to y. Right? That has to be the case. So then I'm just going to do these two integrals. So this guy would give me x squared plus xy squared plus some constant with respect to y. This guy would give me just xy squared plus some other constant with respect to x. Look at all the guys that showed up. There's an x squared, so I write that down. Plus, there's an xy squared, so I write that down. Here's an xy squared, but that's just a repeat, so I don't have to write that down. Add a plus c, and that's your f. So you just integrate. Integrate the first component with respect to x, the second component with respect to y, write down all the guys that show up, and that's going to be your potential function. I think I have another example. It's this is a very important exercise to be able to do quickly, so let's do another example. So assume f is conservative, find its potential function. So notice that this guy has 3 components, so there are 3 things I'm going to care about. I'm going to do method 2 because I like that more. Less going back and forth, you just integrate each piece. So I know my function is going to be the integral of this guy with respect to x. That's what's going to be e to the x cosine y plus some constant. Also, my f is going to be the integral of this guy with respect to y. That's going to give me e to the x cosine y plus some other constant. Also, my f should be the integral of this guy with respect to z. That's just going to give me 2z plus some other constant. And so that means my potential function is e to the x cosine y plus 2z. Plus c, because there's always just a constant there. It'll go away. So that's my potential function for this vector field. Which, the important thing about that guy is that if I need to do a line integral of this guy, if I need to do the integral of f dot dr for this guy, and I know the endpoints, I don't have to actually parameterize and do all that stuff. I just plug the endpoints into this function and subtract them. So we'll stop there. We have one more example to do here, a larger example, but it's worth mentioning at this point that this is the last section needed for our first test. So I'll definitely finish this on Tuesday, and which means that our test will be probably a week after that. So not Tuesday coming, but the next Tuesday. Huh? Which class?
Monday.
Okay. So it's still going to be the next Tuesday. But the review for the test is already online, so you guys can start working on that. You might want to do suggested.
You haven't posted homework on the web work.
Yes, I'll post some homework so you guys can get some practice on this. And if you think you need more practice, do the suggested problems in the syllabus, and we'll stop there.
Okay. What is the potential function for like the gravitational field?